question number 3 of week 14 seminar sheet asks us about molecular absorption lines. Gives the first one at 550 nanometers and the second one as 450 nanometers. Which light has a larger energy? So if you're remembering the little sketch that I've shown you, which I'll just put up now. Essentially, the schematics is you've got your color spectrum, here you've got the associated wavelength in nanometers, and here the associated energy differences that link to these wavelengths. And if you just look up 550 nanometers, which lies here, which will be associated to something like 3.7, so this one will be associated to an energy difference of roughly 3.7 times 10 to the minus 19 joule, as you can see here, for 550, that's going to be 3.7. If you check 450 nanometers lying over here, that will give you an energy difference which is much closer towards 4.5 times 10 to the minus 19 joule. So by just applying this diagram, you can find out that the bluer light will have the larger energy difference as a cause for the light, and the redder light will originate from a smaller energy transition. So what's the energy difference between both of these lines? That needs to be compensated through internal compensation. So if you're thinking about your fluorescence, that's going to be excited by a bluer light. There we are, the bluer light, which has a large energy difference compared to the redder light that goes out. So you'll have 4.5 times 10 to the minus 19 joule you stick in, and you'll get 3.7 times 10 to the minus 19 joule out. So the energy difference that needs to be internally removed through internal conversions is the difference between both. And the difference between both is in our case something around about 0.8 times 10 to the minus 19 joules. So that's the amount of internal conversion that needs to be either radiated away at much lower wavelengths or just distributed throughout the molecular lattice in intermolecular atomic vibrations.